Welcome to the Getting Started with GeoStudio video series. This tutorial introduces how to use the Vadose W product of GeoStudio 2012. This tutorial video has been designed to help walk new users through the basics of setting up a Vadose zone analysis in Vadose W. Vadose W is a rigorous finite element program that links the stress state of the moisture in the ground to the demands of the climate and computes how water moves through the soil-atmosphere interface. So, if you are new to Vadose W and are not sure where to start, you have come to the right place. The main topics that will be covered in the tutorial will be how to create an analysis in Vadose W by using the Define view to set up the analysis, the Solve Manager to solve the numerical analysis, and the options available in Results view to gain a deeper understanding of the analysis. If you are not familiar with GeoStudio products, it is recommended that you start with the tutorial videos for Seep W, Sigma W, or Slope W to gain an understanding of the tools available for drawing your geometry domain, creating sketches, or explanations on basic options that are available in all GeoStudio products. This tutorial video will mainly discuss Vadose W options and tools, where they differ from Seep W, Sigma W, or Slope W. So, let's get started. Early in the development of potential versus actual evaporation theory, a laboratory experiment was conducted in a climate-controlled chamber. The temperature and relative humidity were carefully regulated, and the evaporation from both an open pan of water and a sandy column of soil was monitored. This Vadose W tutorial involves a simulation of this laboratory experiment. The numerical model is quite simple and consists of a one-dimensional column with a total height of 30 centimeters. The top of the column uses a special type of region called a surface region. Climate boundary conditions can only be applied to surface regions, so all Vadose W models must use this type of region across the ground surface. The initial temperature of the soil profile will be specified as a material activation property of 38 degrees Celsius, and a water table will be used to specify the initial pressures in the column. The model will run for a total duration of 40 days, with the climate function including potential evaporation, temperature, and relative humidity that was measured and monitored within the controlled climate chamber. It's interesting to note, from this simple example, how much information and understanding you can get by setting up a simple analysis to test theories and conduct preliminary modeling before moving into a full two-dimensional simulation. We will start with our soil region drawn and the Keyin Analyses window open, with the Vadose W transient coupled analysis chosen. As noted earlier, we will define our initial pore water pressure conditions using a water table, and we will leave the initial temperature condition to none. We will leave the convergence settings as they have been defined here, and then take a look at the Time tab. Here we have defined a total duration of 40 days with daily time steps. We have also activated adaptive time stepping, which is usually required in a Vadose W analysis. The adaptive time stepping has been defined using a minimum time step of 100 seconds and a maximum of 8,640 seconds, or approximately 2.5 hours. Control of the adaptive time stepping is set to allow a maximum change in head of 5% between any two time steps. Now we will return to our drawing page and see that a region has already been drawn for us. Note, the column is still missing the surface layer required by the Vadose W analysis. We will go to Draw, Surface Layers, and change the number of layers to 1. Now we can choose all of the surface nodes that we would like the surface layer to be added to. Here we will simply drag a box over both of the surface nodes of our column, since we want the single layer to cover the entire column. We will enter a layer thickness of 0.01 meter. Next, we will add the material properties for our soil material. We will go to Keyin, Materials, and add a new material to the window. For this analysis, we will use the simplified thermal material model. All of our functions have already been defined, so we will simply open the ellipsis buttons for each to view the function that we will be using. For more information on how to create these functions, please visit the Introduction to SEEP-W or the Estimating Hydraulic Functions tutorial videos. The thermal properties will be set to 1.4 joules per second per meter per degree Celsius for both the unfrozen and frozen thermal conductivities, and the unfrozen and frozen volumetric heat capacities will be set to 2 times 10 to the 6 joules per cubic meter per degree Celsius. Remember, the activation temperature for this scenario needs to be defined as 38 degrees Celsius. Now we can add the Beaver Creek sand material to both the region and the surface layer. Next, we will take a look at our predefined climate boundary condition. We will go to Draw Boundary Conditions and open the Keyin window. Here we can see that a climate function for the University of Saskatchewan has already been defined. We can click on the ellipsis button to see the variables within the function. In Vadose W, climate data is defined as a dataset. This data was copied into Vadose W from a spreadsheet with information from the laboratory experiment. Once chosen from the drop-down menu, we can add the boundary condition to the surface line of our surface layer. Now we will enter the information for our initial water table so that the initial pore water pressure condition is defined. We will go to Keyin, Initial Water Table. Here we will add the X and Y coordinates for our initial water table that is at an elevation of 0.29 meters. Lastly, we can review the finite element mesh and make any necessary adjustments. When we go to Draw Mesh Properties, we can see that the global element size is currently set to 0.066 meters. Since we are conducting a one-dimensional column analysis, we want to control the mesh to use a single element in the X direction with further refinement in the Y direction. We will click on the bottom line of the domain and choose the Number of Divisions option from the drop-down menu. We will force the number of divisions to be 1 or a single element width. Next, we will click on the geometry line on the left of the column and choose the Length of option from the drop-down menu with an element length of 0.01 meter. We can also edit the number of elements in the surface layer in this window by clicking on the surface layer and entering the number of elements in the vertical direction we would like, which will be 2 in this example. Now we are ready to solve the analysis by toggling on the analysis and clicking the Start button. This analysis will take a few minutes to simulate the results, so we will jump ahead to the end of the simulation. Once solved, we can see the total head contours for day 40 of the column. We can change how these contours are visualized by going to the Draw Contours button. Here we can change the contour shading, add or remove a legend, change the starting or ending contours being viewed, or add new contour types using the drop-down menus. Next, we will create some graphs in the Draw Graph window to help better understand our results. The first graph we will see by default is the X conductivity versus matrix suction graph that helps us understand our convergence. For more information on convergence criteria and this graph, please refer to the Convergence and UR tutorial video for SEEP-W. We will add a new graph to look at the cumulative potential evaporation for our column. We will choose the surface region nodes for the top of the surface layer and simply choose one of the two nodes as our location. We will then choose the climate BC, cumulative potential evaporation versus time, and choose all time steps. Now we can see what the cumulative potential evaporation for this node was over our analysis. We will now choose to compare this graph to the actual evaporation that was experienced at this node. We will add another graph and choose to look at the same surface region node. We will now choose the cumulative actual evaporation from the drop-down menu. Now, to see both graphs on the same visual window, we will hold down our Control button on the keyboard and select the potential evaporation graph. Now we can see that the potential and actual evaporation were equal for the first few time steps, but then the actual evaporation began to drop off given drying conditions at the soil surface. Next, we will add a matrix suction versus time graph by choosing the nodes option and the same top node as our location. We will then go to pore pressure, log matrix suction versus time. Here we can see the increase in suction and note where the actual evaporation dropped away from the potential evaporation is similar to when the increase in matrix suction occurs. The water balance graphs can be used to determine if a good numerical solution was reached. The water balance error graph is the first graph we will review. If the water balance error is minimal, it is a strong indication that the model has solved well. We will also create a water balance evaporation graph and a water balance change in storage graph. We will then select all three graphs to view in our window. In this case, the amount of water considered lost from storage is equal to the amount of water that left the profile due to evaporation. More information on other options available in Results View can be viewed in the SEEP-W, Sigma-W, or Slope-W tutorial videos. We have now reached the end of this introductory tutorial. Note that not all of the powerful features of Vadose W 2012 have been used or discussed here. Further information on each command can be found in the online help, supporting documentation for Vadose W, as well as in other tutorial videos of the Getting Started with GeoStudio video series. Thank you for watching.